So knowing what we know about the Nagasaki Tower in the movie Die Hard, it's about 150 meters tall. So, John McClane has the spool and it hooks on to right here. He's hanging over the side of the building. Biggest problem in all this becomes that, in reality, the spool should have never hooked. The net torque that it exerts, that in the position that it's specifically in the scene, would be too great for it to be hooked on the wall. It would just simply pull right over the wall, like it actually does after a moment in the scene, and he would fall to his death much before he has a chance to shoot the window and swing his way in. So the real question is, how much time did he actually have? After analyzing the scene, we can see that he has way too much time. He's falling for a good 3 to 4 seconds before he stops the first time and the spool initially breaks off the wall following the explosion. This is not correct whatsoever because he only falls 4 or 5 stories, which is equivalent to about 15 meters. Once the spool breaks, he falls further down to what looks to be about 10 stories, or like 12. It feels right, which is 36 meters. We can find the potential energy at both of these points with reference to the 0 level. So at this point, when he's at 15 meters, he has before we do this, we have to consider the fact that John McClane is most likely in this scene roughly 80 kilograms. Bruce Willis is about 5'8". He looks like he's like 180, so we'll call him 80 kilograms. Anyways, so we're gonna take that, and so we're gonna find the potential energy at 15 meters from this level up here, which equals 80 times 10 times 150 minus 15. Because we can also acknowledge the fact that this is 150 meters. Anyways, we can take that and compare it to its original potential energy, which is 80 times 10 times 150. The potential energy at 15 meters plus the kinetic energy he's achieved, and when we neglect friction, is equal to the potential energy he has at the top of the building. When we calculate for both, times 15, it's got 108 kilojoules of energy. Kilojoules of potential, mind you. Plus his kinetic energy equals his initial potential energy, which is 150 times 80 times 10 which is a whopping 120 kilojoules of potential energy. All this implies that his kinetic energy at the moment is 12,000 joules or 12 kilojoules. So if we were to calculate his velocity at this point, it would be 12,000 equals 1/2 mv squared. Multiply by 2. Divide by 80. Gets v squared. Then square root that, which would give you 17.32 meters per second. So it's not necessarily the speed aspect at this point that we're concerned about. What we're more concerned about is that the time it took him to fall in this scene is largely incorrect, because it appears to be about 3 to 4 seconds. When in reality, if we solve for time using the first kinematic equation, 17.32 meters per second equals 0 meters per second plus, and technically this is a negative velocity, but for the sake of ease, I'm just considering it as a positive velocity, plus 10 times the time, 10 being our acceleration due to gravity. So, divide this out. This obviously doesn't exist. You get 1.732 seconds, which is less than half of the time shown in the film. Furthermore, building off of this idea, it seems to take an incredible amount of time for him to fall, following the spool becoming unattached from the wall, and he starts to accelerate again. So, knowing we know that U0, the potential energy at the top, is 120,000 joules, we also know that he fell about 12 stories, which is about 36 meters, which means his potential energy at that point is going to be 80 times 10 times 150 minus 36, which is 114, if I'm not mistaken. Multiply that all together, you get 91,200 joules of energy, or 91.2 kilojoules. Again, we'll do the same amount of math. 120,000 joules equals the potential at this point, plus the kinetic energy at that point. So 120,000 minus 91,200 is, so that's 28,800 joules of kinetic energy, which, if we set that equal to 1/2 MVK, now when we find his velocity, we're gonna, because there's technically a momentary pause, we would have to start over at 0 from the reference level when he after falling 15 more meters. But in reality, that pause shouldn't have technically happened, so in the case of doing the realism math, we don't have to account for it. So 28.8 equals 1/2 mv squared. 57.6 equals 80 v squared. 57.6 divided by 80 equals 57.6 divided by 80 equals 720. Remember, we gotta square root that, so the velocity becomes 720, 26.83 meters per second. And again, with the other problem, we already exemplified that the amount of time that he takes to fall is unnecessary. So at this point, we can move on to looking at how the net torque exerted on the on the spool, and the fact that it pauses to begin, that it gets stuck on there, is impossible. Technically, we could assume that the spool is like 0.5 meters in diameter, and then do the math using a modified like version of a pulley system, in which the corner of the wall acts as the pulley wheel, whatever, and each end McLean's the weight on one side, this is the weight on the other side. All you need to know in reality is that when it stacks up against the wall like this, it's up against the wall like this. First of all, the spool is above the wall. Second of all, the end of the fire hose is also at the top of the spool, which means that the net force exerted on this is gonna go this way relative to the system. Just doesn't make sense at first when you look at it. But when you think about how the wall was slightly above it. That's why it's going to do that. The wall was just ever so slightly above it. So it's going to pull up like that due to John McLean's weight acting here on the bottom. And it should pretty much immediately just pull right over, giving no pause, no time to shoot open the window, and having John McLean fall to his death. So sad. At that point, we can assume that at the very bottom of the tower will be 120,000 joules of kinetic energy, which equals, I don't even have to do the math on that one, I know it's 3,000 square root of 3,000 equals v squared. Okay, that one I do have to use the calculator. 54.77 meters per second. Now, we're all probably wondering, how does this relate? Well, when he hits the ground, obviously he's going really fast. So, we can put this in terms of momentum, say that progress is equal to 80 times his velocity. Therefore, we can assume that he has 4.3 4,381.78 Newton seconds of impulse. And obviously when we write that out now, we have force times time equals that divided by the amount of time when he hits the ground to find the force applied. So we can assume that the amount of time that it takes him for the force to act on him when he hits the ground is marginal. We'll just say for all intensive purposes that it's 0.1 meters per second. So when we clear that, I mean, you can do the math in your head. Just bring decimal place over. It's 43,817.8 newtons when he hits the ground. So, in other words, in the most morbid sense humanly possible, John McClane no longer exists.